All right, this is the first lesson of Module 7. We're calling it 7.0 because parts of this actually are things that you've seen before. Combining like terms is stuff you've seen in middle school, and we've actually covered a little bit earlier in the course as well. Here are the objectives if you want to see what we're doing. And there are some vocabulary words to get us started here, just to remind us of some important things. So, monomial, mono refers to one, so that's something that just has one term. Binomial, like a bicycle with two wheels, is something that has two terms. And there are some little examples down here. So 2x plus 3y would be something with two terms. Trinomial is something with three terms. Triangle has three sides. Tri refers to three, so three terms. One, two, three. So once it's separated by a side, then we normally say that's an extra term. And polynomial in general just refers to any sum of monomials, which could be more than three terms, could be four terms, etc. But it could equally refer to any one of these ones here as well. And when we combine in terms, we need to make sure that they're like terms. So all these are like terms. We've got xy here, xy, xy, and we have different numbers at the start. A squared b, a squared b, a squared b. They're all examples of like terms, and you can certainly add those together. 2x plus 19a, you cannot add together because they're not the same letter. And even though they both have w's here, one of these is w and one is w squared, they are also not considered like terms. If this was 4w squared, then I could definitely simplify this. Or if this was just 10w, then I could simplify this as well. All right, let's take a look at lesson 7. But basically, we're looking at combining like terms through adding and subtracting. We'll look at some word problems, but we're also going to introduce algebra tiles today as well. Now, there is some little activities here, but we're going to skip these ones just because we've seen these ones before. And we're going to get straight to our algebra tiles. So the thing with algebra tiles is we have different shapes that we use for different objects. So essentially, we have what I call big squares, which are our x squareds. We have x's, which are our rectangles. And then we have little squares, which are our single units. Now, it said group them all together. So the idea was, as I'm looking at this, I can see that I have three big squares, and therefore this would be 3x squared. You can see that I have two x's here, therefore this would be 2x. And you can see that I have four single ones here, which would be 4. So if I was to work out what all this is, I would say that it's 3x squared plus 2x plus 4. And the reason we do it with shapes is you wouldn't be tempted to want to add these two things together. You can see that these clearly are not the same visually. And for that reason, you would try doing something like 1, 2, 3, 4, 5 here, even though they both have an x in. So as they're clearly different shapes, we're not like terms. And for that reason, we don't add them together. So 3x squared plus 2x plus 4. And they made it even easier for you to see what this looks like. Now, also, as we're writing out our answers, we always start with the biggest shape first, or the highest power. So the power or the degree, this is the exponent here. So this is 2. Remember, we don't see an exponent, it's 1. And this doesn't have any letters at all. So technically, this is an exponent of 0. So if I'm writing this 3x squared, we use shift and 6 to get the exponent. And then we can just carry on typing. Plus 2x plus 4. And I can confirm that that is a correct answer. Also, we can do this in reverse. Sometimes you might be asked to make this. So x squared just means I got one big square. 2x means I have two x's. And 3 just means that I have 3 little ones. There we go. That's all good. Right now, it's not super obvious why we're doing all the stuff with algebra tiles, but they become really important as we get later into this unit as we're trying to solve problems. So to use them now is really helpful. All right, let's see what we got here. So I can see for this question here that there are 3x squareds, 2x's, and 4 little ones. So, well, I notice these aren't x squareds. These are actually a squareds. So I have 3a squared. I have 2a. And then at the end, I have 4 little ones. There we go. Perfect. And looks like we got another one to do. So 2 big squares. So 2a squared. I have 1, 2, 3, 4 rectangles, so 4a. And it looks like I got 5 little squares there, so plus 5. And hopefully that's right as well. Yep. And then we can start doing things like we work out the total. So total means we're adding these things together. Now I can do this just by looking at the picture. I can see that in total here, I got 5 big squares. So I can put 5a squared. Now I can also do this algebraically as well by looking at these numbers here, 3a squared and 2a squared. Just adding the numbers at the start, 3 add 2 tells me I have 5 of that object, which is a squared. 1, 2, 3, 4, 5, 6. So it looks like I have 6a. And I can also do that quickly from here as well. 2 add 4 gives me 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. I can see that I got 9 little squares. And I could have also done that from here. Positive 4 add positive 5 is positive 9. And you can see that they're grouping those like terms together. So by doing it with visuals first, it helps it make it a little bit more easy as you're doing examples that just have letters later. Now, there are some codes here for IXL that I would strongly recommend that you look at so you can get used to these ideas of what these shapes actually look like, but also it introduces the ideas of negatives as well. So if we have negatives, they tend to do them in a different color, and they tend to give you a little negative sign on here as well, so you can see exactly what they are. What if we put the following letters into the box? How many would we have? So when we look at X's, some people just go, I got 1, 2, 3. But more importantly, it's how many of each we have. So 3 add 2 add 4. That would be 9x. It might just want 9 here. I'm not sure, actually. Oh, no, I can see it put 9x at the top, so that's fine. When we don't have a number, that means 1. So 7 add 1 is going to be 8. So 8y. And at the bottom with the z's, 4 plus 1 plus 5 is 10. So I'm going to put 10z. There we go. And we add them all together. What we can't do, though, is add those together individually. I certainly can't say 9 add 8 plus 10 is 27 because these are different letters. Now, having done this for a while, you then start to get to just more of an algebraic question where we're looking at things like this. So as we're adding, what I'm noticing is I got certain letters that are the same here. So they're the ones I want to add to get those like terms. So 3 plus 2, that's going to be 5. So I have 5x. Now be careful, don't just say 4 add 5 here. Make sure you look at the sign here. So this is a positive 4, which is just 4, add 5. But if that was negative, then this would be negative 4 add 5. So we have to be a little careful here. So 4 add 5 is 9. So I should have 9y. And once again, don't try and add those together. Don't try saying it's 14. It's just 5 of the x and 9 of the y. And I can confirm that that one is correct. Ooh, this one looks a little bit longer. I always like to do my letters first. So I can see I got positive 3 plus 2, which is 5. So 5a. I have 7b and then take away 7b. So 7 take away 7 is 0. So I'm not going to put 0b. I'm just going to leave it at that. And then right at the start, I got 8 take away 5, which is 3. So I would put positive 3. And there is some recommendations of questions you can practice. Now, we are going to get word problems as well. So let's see what we got here. During a 7-year period, the amount in millions of dollars spent each year on buying new vehicles, N, and used vehicles, U, by the United States resident is shown below. Here we go. Here's the amount for new cars. Here's the amount for used cars. Write a polynomial in standard form. So standard form was when the powers decrease. So we start off with a power of, for this question, 3, then 2, then 1, and so on. That represents the total amount spent each year on buying new and used vehicles. So as it says that word total again, and I'm adding these together. Now, the way they've lined this up is not particularly helpful because this is t cubed and this is t squared. So I cannot add these together. In fact, I can only see one term that even has a cubed in here. So I'm just going to fill in that one first. T cubed, cubed, there we go. Now, these two I can add together. 0.06 add negative 0.38. You can check on decimals if you wish, but I promise you that it's this. And then the same for the t's. I got positive 0.1, and I'm going to add positive 1.5 to it. That would be positive 2.5. And then at the end here, I got positive 42 and positive 17. So if I add those together, that will give me positive 59. The length of an electric cable can be modeled by this. The length of a second cable is this. Write a polynomial that represents the difference in the lengths of the two cables. So when we're talking about difference, that means we're going to subtract the difference, subtract the distances. So if I'm subtracting here, 7 take away 12, I know is negative 5. So that would be negative 5x squared. 5 take away -7. We've got to be a little careful when we're doing that one. That one would be 12. And we should be checking on Desmos just to make sure. And 8 take away 3 is 5. So plus 5. Sometimes it's not always clear which way around we should subtract. So in not normal, I'm just doing the first one, take away the second one, unless it specifies otherwise. Or sometimes you do the biggest, take away the smallest, but that's not always easy to see when they're expressions rather than numbers. It might seem that 12x squared is the bigger of the two, but it might not necessarily be true. Company produces X units of a product. C of X represents the total cost. All right, that's the total cost. R of X represents the revenue. Okay. And functions and modeled as below. The profit is the difference between the revenue and the cost. Where P of X, this time it does tell us which way around to subtract. It wants us to do this one, take away this one. What is the total profit? So I'm starting with this one here. I don't see any other x squareds up here, so I know that it must start with -0.5 x squared because there's nothing to combine it with. And then for the second part of the question, I'm looking at my x's. So I got positive 800, and I got to take away 300, which should be 500. Notice multiple choice answers, they do have positive 500, and they also have negative 500 up there as well. So if you did 300 take away 800, for example, you'd end up with negative 500. So reading's really important for this. And then the last part, I got negative 100, subtract positive 250. If you're not sure, you could always use Desmos. I know for this one, though, this is going to be negative 350. And for that reason, it would be answer B. And last one, perimeter. We've had perimeter quite a few times so far this year. Perimeter is when you add all the sides together. So as I'm looking at it, I'm just looking for those like terms. So 5x, 2x, 2x. When I add those together, that is 9x. -3, add 7 is positive 4. Add -2 is positive 2. So this should be 9x plus 2. And I believe this one does self-check. No, I guess I was wrong. I thought that one checked actually by itself. And hopefully those answers that I mentioned, those same answers there, they certainly look very similar. And the last part of today's lesson is multiplying with algebra tiles. Now, this is more for later on in our course. So this is more for around, I think it's lesson 6.3, lesson 6.4. But obviously 3 times 2 is 6, but I want to visually show you why. So I put 3 tiles across the top, 2 down the side, and if you notice that the area that it creates, the little tiles in the middle here, there's 6 tiles here. Notice these 6 tiles are as wide as this across the top, and notice it's as tall as this going down the side. Now, obviously, we don't really need help on working out 3 times 2. As we start working out things with algebra in them, then we might need a little bit of help. So this question works out 3 times 2x. There's 3, there's 2x. And you can see I got 2 x's and 3 little ones. If I fill in the shape to make it as wide as this and as tall as this, you can see that I have 6 x's in the middle. Now, we should already know that. 3 times 2 is obviously 6. As there's an x, this is 6x. And if I go a little bit more complicated using the distributive rule, let me just move this out of the way. 4 times 3x minus 2, there's 4. There's 3x. There's 2 negatives. If I start to fill in this shape here, I would end up with 12 little x's here. And then I got 8 negatives here. Now, the reason I filled in negatives here is because these are negatives. But more so, probably more importantly, these are positives. And if I multiply a positive by a negative, I should know that I get a negative. If I was to multiply a negative with another negative, then that would be a positive. So if this was -1 over here, I would actually fill this in as +1. And you can see just by the distributive, 4 times 3 is 12, so 12x. 4 times -2 is -8. So that's all things that we've done before. What we haven't done before, though, is trying to answer a question that uses 2 binomials. So if I'm trying to work out 2x plus 1 times x plus 3, I'm going to use that same idea. I'm going to put one of the expressions across the top, one of them down the side, and then I'm going to fill in the gaps, and then whatever the space is in the middle, that'll be the answer to this question. So using algebra tiles, I can put out 2x plus 1. Let me just go back to the slide here so you can see how this is actually done. It's been a while since I've done this. I'm hoping I can remember. Here we go. So I click on algebra, click on algebra tiles, and then I can just drag whatever I need. So there's an x, there's another x, and there's a 1. And I can probably zoom in so it's a little easier to see as well. There we go. And I was also trying to work out x plus 3. So down the side, I'm just going to do that same thing. I'm going to put x plus 3. And there's two different x's. I always want the x to be as snug as I can to the side here. So this time, as I'm going down the side, I put the rectangle that's kind of going downwards as well. So I want a shape that's going to be as wide as this, but as also going to be as tall as this. Now, I'm not sure if it'll let me do this on here. Here we go. It looks like it might do. Basically, I'm going to be splitting this into 4 separate answers. So the first thing I'm doing right now is I'm just trying to break it into those 4 little pieces so you can see them a little bit easier. There we go. And then down there as well. So this space here, notice how there's 4 parts. 1, 2, 3, 4. And as I fill this in, this part here, I'm going to fill in with big squares, x squares. The 2 side pieces at the side here, I'm going to fill in with rectangles. And then the piece here at the side here, I'm going to fill in with little squares. So let's see how that works. So there's 1 big square. Oh, that was pretty easy. 2 big squares. Now, just by looking at this shape here now, you can see that that's going to be that little piece right there. And as I'm doing these here, I'm hoping that you can see, well, there's 1, 2, and it looks like I just need a couple more rows of these. 3, 4. I didn't do it quite as neat as I could have done. There's a small little gap in there, but I think we can see that we can fit 6 rectangles in here. And then in that last space, 1, 2. And before I fill that last one in, I just want to show you, you can also use this trick here of just copying something. And then you don't have to keep going backwards and forwards if necessary. And if you want to, you can also highlight things. So if I wanted 6 more rectangles and 3 little squares, I could actually highlight bigger pieces if I needed to. But I'm going to stop right there. So the answer to this question, 2x plus 1 times x plus 3, is these pieces in the middle here, not the outside, just these pieces here. So actually, if I can, I'm going to try and just move those out of the way. There we go. And I'm going to zoom in so you can see what we got here. So just looking at all the things in order, I have 2 big squares, so 2x squared. I have 1, 2, 3, 4, 5, 6, 7 x's, so plus 7x. And then I have 3 little squares at the end, which would be plus 3. That's how you can work out the question. Now, we're going to do it by algebra because we want that idea of when we're multiplying 2 terms by 2 terms, we end up with 4 terms because eventually we're going to be doing these questions backwards. When we have 4 terms, we need to be able to get back to the original 2 terms and 2 terms. And that can be kind of difficult if we're not used to using this procedure. So I'm going to work through these last slides and just show you what I did again. So I put 2x plus 1 across the top. I put x plus 3 down the side. And then I started to fill in my big squares across the top here. Then I filled in my standing up rectangles at the top left here. And basically, notice now I filled up everything that relates to this shape here. Then I'm just going to move to the bottom row and fill in everything that goes with the 3's. So as there was 3 squares, I needed 3 rows of rectangles to match up with this. And then in the very far corner, I just filled in my little 1's. And then I added up what I actually had, which should be on that next slide. There you go. 2x squared plus 7x plus 3. There are more of these that are going to feature in Activity 7.0. And if you're watching this after the lesson, then that activity will already be open. If you're watching it early, that will not be open right now. And just remember, today's objective was to work on adding and subtracting terms. And I think we managed to do that in several different ways. We looked at how to do it with just algebraic expressions, with pictures, with tiles, and then right at the end, we started to look at how we can do that when we're trying to multiply questions, but we were still adding and subtracting those terms at the very end of the question as well. And we'll also do more of this in the next lesson as well, but with parentheses. But for right now, that's the end of lesson 7.0.